So, Bismillahirrahmanirrahim. Today we will discuss the equilibrium. Equilibrium. So, equilibrium means when a body is stable. Stable means when the net force on a body is equal to 0. So if we have, for example, an object and we apply a force of 5 newtons here, and we apply a force and 5 Newton force in this direction. So if we have this object and we apply two forces, one is 5 newtons in this direction, another one is with the same magnitude but opposite direction, means this is then direction wise this is the minus 5 newtons. So the minus is representing the direction. So although there are two forces acting on this object, but this object will not move because they will cancel each other, and this object will be in equilibrium. Now we have two different types of equilibrium. So in one case, so we have a linear case. So a linear case is when we apply a force like here. This is a linear case, so we apply a force which will cause the acceleration, and the net force here on this object is 0. So the total net force on the system when it's 0, so this is the equilibrium. So first we will discuss the linear case, and then we will talk about the rotational. So first we talk about the linear case. So when net force is 0, so this is a linear force. So this is also another statement of the Newton's first law of motion. So Newton's first law of motion states that when a body when there is no external force on an object, so if it's in the state of rest, it will always remain in the state of rest. If it's moving with a uniform speed, it will always be moving with the uniform speed unless there is an external force that's acting on it. So the net force on an object is 0. So this is also another form of so this is the Newton's first law. So if the force is 0, that means according to Newton's first law and also according to the Newton's second law, the acceleration will be 0. So if the acceleration is 0, because F equals ma according to the Newton's second law of motion, so that means, so if the acceleration is 0, then we have two possibilities. Either the velocity is 0, or the velocity is uniform. So if we have the acceleration is 0, it means either the velocity is 0, means the body is not moving, or if the acceleration is 0, that also means that a body is moving with a uniform velocity. It's not changing. So if it's not changing with time, so the acceleration is 0. So we can also write, so we have the momentum is 0, because here momentum is mass multiplied by velocity. If the velocity is 0, usually the mass is constant in the classical physics. In the Newtonian physics, the mass is always constant. The mass changes when something is moving close to the speed of light, but right now we don't talk about the speed of light in the relativistic things. So the mass is always constant. So here, if the velocity is 0, it means the momentum is also 0. So if the velocity is uniform, that means momentum is also uniform. So which means the change in velocities is 0, or the change in momentum is 0. So if the velocity is 0 or uniform, it means the change in velocity is 0 or the change in momentum is 0. So this here is the first condition of equilibrium. So the first condition of equilibrium, so we just said that equilibrium is something when the net force on a body is 0. So if the net force is 0, it means the acceleration is 0. So if the acceleration is 0, that means either the velocity is 0 or the velocity is uniform. So if the velocity is 0, that also means in the classical physics that the momentum is 0. If the momentum is, so the momentum is 0 or uniform, so we can also say that the change in velocity is 0 or the change in momentum is 0. So this is the first condition of equilibrium, so which is for the linear case. And now in the previous lecture we talked about the turning effect of a force, which was torque. So the torque is usually causing the rotation. So we have, now we talk about the rotation. So this side is the first condition of the equilibrium, and now we talk about the rotational case. So this is the second condition, which means the net torque, so this is the net torque or sum of all the torques, is 0. That means that the angular acceleration is also 0. So we have the similar case. So for the linear case, we have the force is causing the acceleration, and here in the rotational cases, rotation here, the torque is equivalent to the force here, and this alpha is the angular acceleration, which is equivalent to the linear acceleration in this case. So that means here again we have the angular speed is 0. So if the angular acceleration is 0, that means that the angular speed is 0 or the angular speed is uniform, just like we discussed in the linear case. So that also means that the angular momentum, which is represented by L, is 0 or angular momentum is uniform. Uniform. So that means the torque or change of angular momentum with respect to time is 0. So here we talk about the change in velocity here, and then here we have the change in the angular speed. So the angular speed is equivalent to, here in the linear case, is the linear velocity here, and here momentum is the for the momentum we have the equivalent here, which is the angular momentum here. So the torque is equal to the change in the angular momentum with respect to time. If it's 0, so that's the so these are this condition will be applied here. So if the net torque is 0, since the torque is talking about the rotation, for example, if we in the previous lecture, so we discussed about the door. So if we apply a force, so this will cause anti-clockwise torque. If we apply force in this direction, this will cause the clockwise torque. So which means that the sum of the clockwise torque is equal to the sum of anti-clockwise torque. So this is the second condition of equilibrium. So for the first condition of equilibrium, we saw when the net force is 0. So when the net force and the is 0, for example, here we take an example here. So we have the force 5 Newton force, and we have the opposite force here, which is in the same line of action, is the same. So this, well, they will cancel each other. So the net force on an object will be 0, and this object will be in equilibrium. So this was the first condition for equilibrium, which is the linear case. And now we come to the non-linear case, which is the rotation here. And here we talk about the torques. So here, if the total net torque on a body is 0, that means that the clockwise torque is equal to the anti-clockwise torque, and this is the second condition of equilibrium. Since here we talked about the first condition of equilibrium and second condition of equilibrium, now we take an example, and in the example we discuss the first condition of equilibrium and the second condition of equilibrium. So here we have a string which is attached to fixed points, or we can say this string is attached to two walls. So when we hang, so here we have an object. We hang this object here, which has a mass m, and because of this mass, there will be a gravitational force in the y minus negative y direction. So this is the weight of the object, which is here is 10 newtons. 10 newtons. So because of this gravitational force, there will be a tension in this string here, and then we will have also a tension here. So we will have a tension here, we will have a tension here. So we want to know, so this string here is making 15 degrees angle. So this is 15 degrees angle, and right now we want to know what is the tension here, and we want to know, so what is the tension here. So in the previous lecture, when we were talking about the vectors, we said that we can split the vectors into two perpendicular components in order to solve the problems. Here we can see here this tension, which is a force in the string. We want to know what's the force here. So we have here on this side, so we have the x-axis, we have the minus x, we have the y, and then we have the minus y. So on this side, so we just split. So this is the tx, so this is the tx, this is the ty. So this is the minus tx, and this is the plus ty, and the force, the gravitational force here, since it's in the minus y direction, so this is minus 10. So here this weight of this object is negative. Right now we will see, since we said that all the forces must be 0 according to equilibrium, because right now the system here is in equilibrium. Although there are forces, but they are cancelling each other. We have a gravitational force, and then we have the tension in a string. They are cancelling each other. So you can use the first state of equilibrium, which is the net force on the object will be 0. So now we have two types of forces. One is in the horizontal axis, and other one is in the vertical axis. So the horizontal forces here, they are Fx is 0. So this is the first condition of equilibrium. So the first condition of equilibrium, so what are the forces? We have the Tx, and then we have the minus Tx. So the total force is the Tx plus minus Tx. So they will cancel each other, and there is no force in this direction, so the sum is 0. And now we come to the y direction. So this must also be 0 according to the first condition of equilibrium. So in the y direction, so we have ty, so we have ty plus ty, and then minus or plus, this is the minus w, this is 0. So we have the 2y, 2ty equals minus w. So this is if it goes to the other side, it will be plus. So we have 2t y sine of theta, because in the y direction here. So we have w, since we are interested only in the tension here, which is in the y direction. So ty equals w, what is the weight of the object, which is 10 newtons, and then we have the 2 here, and then we have the sine of 15. Sine of 15 is 1 by 4, and the answer is 20 newtons. So here what we see, that the weight of the object here is the 10 newtons, but here the tension is larger here. That's why it's holding the system. Now this is the, we discussed that if the angle is 15 degrees, and now we discuss what if the angle is 30 degrees. So right now this angle is not 15, so we discuss a second case. We change the angle, so this is now 30 degrees. So again, so everything is the same. We have the tension, we split it into the y components of the tension and also the x component of the tension. And here we see that the tension here is larger than the weight. If the weight is larger than the tension, then the string will just break. So the net force, and again in the x direction, is 0. So there is no force and there is nothing happening in the x direction. So we just come to the y direction. So the net force in y direction, that also must be 0. So again we have the ty plus minus weight of the object. So we have this force in the y direction, we have this force in the y direction, and then we have the minus weight, which is in the opposite direction. So we have the ty equals w, and 2ty sine of theta equals w. So we are interested in ty, which is the force, equals w2 sine of theta. And here the ty is, if we put the values here, so we have the 10 newtons here, so we put 10 newtons and 30 degrees here, so we will get 10 newtons here. So what we see here, that if we increase this angle, so the tension will decrease. So if we increase the angle, so the tension will decrease, and if we further increase the tension, the tension in the string will break. And now we discuss the example in which we will talk about, or we discuss the second condition of equilibrium in which the torques will be involved. So we have a rod which is balanced here, and we have 10 kgs. This is 10 kgs mass is hanging here, and on the other side we have another mass that is not known. So this is, they will cause the M1G. M1G is the gravitational force which is because of this mass, and we have the M2G here. And the distance, which is the moment arm for this one here, the R1 equals 16 centimeter, and this distance here is 20 centimeter. So what we see here, that the distance, the moment arm for this mass is here is smaller than this one. So we want to know what is the mass that is hanging here. Since this distance is larger, so this mass should be smaller than this mass, and we will try to find out. So we use the second condition of equilibrium. So we have the second condition of equilibrium. So the second condition of equilibrium is that the torque, the clockwise torque, is equal to the anti-clockwise torque. So here, this weight, or this force here, the gravitational force, because of this mass, is causing the anti-clockwise torque, and this one is trying to cause the clockwise torque. So this one is here trying to move this system in this direction, and here it's the anti-clockwise torque, but they are equal since the net torque is 0 according to the second condition of equilibrium. So we want to know what is the mass of this object here. So we have the RF1 equals R2 F2. So what is the R1? And then we have the F1 is here, and then we have the F2 here. So we have the 16 multiplied by mg, m1g equals, we have the 20 multiplied by m2g. So we have the 4 m1g equals m1 equals 5 m2. So we are interested in m2, so the m2 equals 8 kilograms. So they, since we can see here, they are cancelling each other. So we can see here, since this distance is larger, in order to balance the system, this mass should be smaller than this one, and we can see here it's the 8 kgs. What other thing we noticed, that if we want to use the second condition of equilibrium, since the gravitational, whenever the gravity is involved, since the gravitational force is mg, the mass into the gravitational acceleration, since the gravitational acceleration is always the same for these two objects, so they will cancel each other. So for exams, you can use the short formula, which will be m1 r1 equals m2 r2. And now we will discuss an example in which the first condition of equilibrium and also the second condition of equilibrium is discussed or used. So here we have a rod or a piece of wood which is again hanging here, and this is the fixed point. So this is the fixed point. So we have a rod here. So the mass of this rod, so this is a rod. So the mass or the weight of this rod is 500 newtons. So since this is there, so there will be, so this is the force, so there will be a tension here. So this is TA, this side is the TA, so this is point A, and this is the point B. So this will also cause the tension here in this system or this string here. So what other thing, so the total distance from here to here is 4 meters. 4 meters. And at the distance of 1.2 here, so this is the 1.2, we have another mass here, which is here we have another mass, and its weight is 300 newtons. Right now, so we want to know that what is the value of TA and what is the value of TB, the tension here in this string, and what is the tension here in this string. We can see here, this is the system, the whole system is in equilibrium, so the total forces and the total torque is 0. But what we see here, there is an additional mass here which is causing this force. So there will be the tension in A will be larger than the tension in B here. So if the tension here is larger, this will try to rotate the object or the system in the anti-clockwise direction. So the first thing that we know in this system is that the TA is larger than the TB. Why? Because we have an additional weight here, which is 300 newtons. So this is the first thing that we know. So the first condition, right now we will use the first condition of equilibrium. So the net force in x direction we don't have to worry about. It is 0 because there is no force in this direction. The only forces that we see here is in the y direction. This force is in the y direction, and this force is in the downward direction, which is in the y direction. TA is upward direction, this is y direction, and this is y direction. So we completely ignore the Fx or the force in the x direction, because the net force is 0, or there is no force at all. So the Fy here, according to the first condition of equilibrium, so the net force in the y direction must also be 0. So what forces are there in the y direction? So we have the TA plus TB minus 300 newtons minus, so we have the TA plus TA, since they are in the opposite direction, so this is minus, so this is also minus, equals 0. So here what we see here, so they are, so this one is upward, so this TA plus TB, they are in upward direction, so we write TA plus TB. Since they are in the opposite direction, so we write so 300 minus 300 and minus 500 newtons. So from this one here, so we can get the TA plus TB equals 800 newtons. So this is the first equation that we get. So the net, so the total tension in these two, the sum of these two is 800 newtons. So this is the equation number 1. Now we use the second condition. of equilibrium so which is the clockwise torque net of the clockwise torque must be equal to the net torque which is in the anti-clockwise torque. So here we will use the force and we will also use these distances, because the torque, we know torque is equal to the force and the distance. So here, since the angle is 90 degrees, so we just completely ignore the angle. Otherwise it's the cross product. So here for the small weight here, the distance is, we can see it's 1.2 meters, and then we have the 4 meters. And here we can also see the distance, which is 2 meters. So for the 1.2 multiplied by 300, which is for the small mass, additional mass, plus 2 multiplied by 500. Why 2? Because this is the middle point here and we have the 2 here. So it's just the 4 is the total, but 2 is the middle point here, and this is equal to the 4 TB. So 4 is the distance and the total distance, and T is the force. So we have the clockwise and the anti-clockwise torque. So we have the 360 plus 1000 equals 4 TB here. So the TB, from this equation we get the TB is equal to 340 newtons. If we use this equation here, since we know now the TB here, the TB is 340 newtons, so we can get the TA from this equation here. So the TA is 800 minus 340. So the TA is 460 newtons. So in the beginning we discussed that since there is an additional force here, so the TA must be larger than the TB. So this is 460 and the TB is 340. So here in this example we discussed, so we used the first condition of equilibrium and also the second condition of equilibrium in order to find out what is the value of TA here and what is the value of TB.